Today, I am going to talk about how solid-state devices or semiconductors work. Now, this is something you don't need to know to use semiconductors, but it's something you're expected to know, and you might find it interesting. So when I talk about transistors down the road, instead of talking about how they act from a physics point of view, I'm going to relate them to valves in a pneumatic or a water circuit. So for example, a diode acts like a check valve. So here's the body of a valve. And we have a closer of some sort, and it's spring loaded. And so if water tries to go that way, it's just going to close it more. But if water tries to go that way, it's going to push on the spring and open it up, and it'll travel that way. So a diode allows current to flow one way, but not the other. So it's a check valve. So a diode, so that is pretty much equal to that. It allows electric current to flow that way, but not that way. This allows water or air to flow that way, but not that way. A transistor, I'll talk about that in a little more detail. Not very many truckers out there, I'm sure, but there's a valve in a truck brake system called a relay valve. Just be very brief because I'm going to explain it in detail later. But that's a valve that I'm just going to draw a block here. We have a little air hose going in here and a big air hose going that way. And a little air going into this relay valve opens the valve and allows a lot of air to flow from one place to another, from an air chamber to the brakes. That's on a truck. Well, that's a transistor. And I'll talk more about that in detail later. Hope you find that interesting when I talk about it. So this is a pneumatically operated valve. A transistor, I'll just draw a bipolar junction transistor here, is a current operated switch. So when I send current from there, the base to the emitter, I get a higher current from the collector to the emitter. So it's basically a current controlled variable resistor. The more current, the less resistance, and the more current I get from there to there. But enough of that. I'll talk about that in detail later. I just want to talk about the physics of how it works, which, like I said, you don't need to know this, but it's something you are expected to know. So let's talk about a little bit of chemistry. I'm not a chemist, so I probably don't get everything 100% correct here, but let's get as close as we can. First, I want to talk about chemical bonds. Let's talk about an ionic bond first. Let's say we have a chlorine atom. Now, a chlorine atom, I'm just going to draw a little circle, and that's what's called the kernel of the atom. This would be the nucleus, which would have all of the protons and neutrons, and all of the electrons except for the outermost layer. So that's called the kernel. So once again, the kernel is the nucleus plus all of the electrons except for the outermost layer of electrons. That outermost layer of electrons is called the valence shell. So we call the electrons shells because they seem to form shells around the nucleus of the atom. It's more complicated than that. It's not worth talking about at this point, but we look at it that way. And so there's one outer shell of electrons, and regardless of the atom, it's going to be most stable if there are 8 electrons in the valence shell. Now, for example, hydrogen has only 1 electron, so it has 1 electron in its valence shell. Helium has 2. Lithium has 3. Lithium is going to have 3 protons, 2 electrons in one shell, and then it's going to make a higher shell that has a 3rd electron. And we can go down the periodic table, and each time we add a proton, we add an electron. And once we get 8 electrons in that second shell, then we start getting more electrons in the next shell. But they arrange themselves in such a way that the outermost shell, regardless of the element, is going to have from 1 to 8 electrons. All the other electrons will be inside part of the kernel. So let's take a chlorine atom, and that's going to have 7 electrons in the outer shell. I'll just draw them like that. And it would like to have 8. And it has a very attractive force. Sometimes they call that negativity because there's a lot of electrons there, although it's not negatively charged. Remember, for every electron we have in the shell, there's a proton in the atom. So it's a neutral atom, but because it has 7 of the possible 8 electrons in the valence shell, it has negativity. And it really wants to fill that shell with an 8th electron. I'm going to just put these a little bit lopsided here to leave a big gap here. Now we're going to take a sodium atom, which I don't know how many total electrons are in a sodium atom. Lithium, I know there's 3, but sodium is the next thing down on the periodic table, next level on the periodic table, and I don't know off the top of my head, but I do know it has 1 electron in the valence shell. So here's sodium. No, Na for sodium. For natrum or something like that, the Latin name for sodium, is going to have 1 electron. It would really like to have 8 or none. It wants to either attract more electrons, but it doesn't have the power to because it doesn't have that negativity to attract another atom to it. So it would much rather give up that electron to another atom. And so what happens if you get sodium and chlorine together, I'm going to draw that as a circle to remind us that this electron is from the sodium atom, and there's the sodium kernel. And so that sodium, supposed to be an A there, that sodium is strongly attracted to this chlorine atom, and that 1 electron fills the valence shell. Now the chlorine atom has 8 electrons around it, and it's happy, and this sodium atom got rid of that electron. Now it's happy, and it forms this very strong bond. Gave up a lot of energy in the process of doing that. Basically, we get a sodium chlorine fire, if you will. It gives up energy, and it becomes an element we call sodium chloride or table salt. That's what's called an ionic bond, where an element with 1 electron basically gives up that electron to another element that has 7 electrons that wants to have 8. They stay bonded together because this sodium atom is bound to this electron, and so we form this structure we call sodium chloride. The next kind of chemical bond I want to talk about is a metallic bond, and this is formed by materials that tend to be to the left side of the periodic table, most of the left side, about 2/3 or 3/4 of the periodic table is going to be your metals, which of course sodium is one. If you put a bunch of sodium atoms together, you get a metallic bond. We'll talk about copper, although they're pretty much the same, but I just keep thinking that sodium is so dang volatile. You get it wet, it explodes. Let's get something safer like copper. Copper has a whole bunch of protons and neutrons and of course the corresponding electrons, but we take the copper kernel and all of its electrons except 1 are in the kernel. So that's your copper kernel, and then we have 1 electron in the valence shell. So could copper form a salt with chlorine, make copper chloride? Oh yes, it could. But we're not going to do that. We're going to just put a whole bunch of copper atoms together. These are all copper atoms, each one having 1 electron, and they form a crystal structure that is such that these electrons in the valence shell don't fit into the structure. So they're free to just float around. Now some people will say they hop from atom to atom. They might even show the electrons going around in circles, and then they hop to that one and go around that one, then hop to that one and go around that one. That's not really what's happening. It's basically a sea of free electrons with copper kernels or copper ions embedded in there. So that's what a metallic bond is like. And since these electrons are free to move around, it's very easy to put a voltage across there and push those electrons across. And so copper, like most metals, are good conductors. And your metals that have only 1 valence electron are your best conductors. Other metals, most of your metals have 2 valence electrons. Many have 3s. Aluminum, one comes to mind, is one that has 3 valence electrons and has less conductivity. So your metals tend to conduct electricity, and they form these metallic bonds. And I didn't mention that, of course, the ionic bond, that's a very tight bond. The electrons held into the valence of that halogen crystal. All of your materials that have 7 electrons in the valence shell are called halogens, meaning salt formers. And so chlorine and sodium forms sodium chloride, a salt. Copper chloride would be a salt. But anyway, they don't conduct electricity because those electrons are bound very strong into that chemical structure. But now we're going to talk about something in between. Now I mentioned that most of the elements, about 2/3, 3/4 to the left side of the periodic table, are metals. And then to the right side are the nonmetals, which will tend to form those ionic bonds. But somewhere in the middle, not in the middle, but to the right of the middle, is one column of materials that have 4 electrons. So here is a column where the materials have 3 electrons in the valence shell. We have aluminum there is one of them. Let's see, aluminum. I don't remember any of the other ones, but you can look at the periodic table. Here we go. There's a periodic table, so you see where they are there. And over here, elements that have 5 valence electrons. One comes to mind as arsenic. I can't think of the other ones off the top of my head, but if you look at the periodic table, there's arsenic, one of the heavier metals in that area. And just notice that in the periodic table, as you get lower, the metal starts spilling over. And even though, well, let's look at these real quickly here. Our materials with 4 valence electrons, we have carbon, silicon, germanium, and then we have tin and lead. Notice that tin and lead are metals. So the metals tend to spill over there, and so even arsenic, I think, is arsenic next to tin? The arsenic's next to tin or next to lead, if you look at the table again. And it's actually a metal. So we get some metals over in here, and most of your metals are over here. So even though this has 4 valence electrons and these have 5, those actually are metals and they act like metals. But these 3 special materials, carbon, germanium, and silicon, are your semiconductors. They neither act like metals or nonmetals. Now, if you put them together, they will form what's called a covalent bond. There's other materials that can form covalent bonds. For example, water is a covalent bond. We have oxygen with 6 electrons in the outer shell, and you get 2 hydrogens with 1 each, and they form a bond that's called a covalent bond, if I remember correctly. If I'm wrong, like I said, I'm not a chemist, but there are other materials that do form covalent bonds. But the semiconductors, carbon, germanium, and silicon are the ones we're most interested in. So let's just use silicon because we can. What's going to happen if we have a silicon atom? It has 4 valence electrons, which I will put out here at equal intervals or equal spacing. And if we put another silicon atom near it, it's going to try to bond with it. And I'm going to draw this kind of cockeyed here. Trying to draw something 3-dimensional in a 2-dimensional space, and it never works. So there's a silicon atom there, and there's another one over here, and it has its 4 valence electrons. I'm going to redraw this later because this is just a preliminary drawing to show how this kind of works. There's another silicon atom, and put one more over here. Now I'm going to draw some lines to show which electrons belong to which atom. So those electrons belong to that atom, those electrons belong to that atom, these electrons belong to that one, and those electrons belong to that one. And finally in the middle we have these 4 electrons belong to the one in the middle. And look what we have here. This one in the middle has how many electrons around it? 1, 2, 3, 4, 5, 6, 7, 8. And if we expand this to where we have more and more silicon atoms, we'll find that every single silicon atom both takes and gives up 4 electrons. So it doesn't form an ionic bond, and it doesn't form a metallic bond. It forms a covalent bond. So once again, we have each atom with 8 electrons around it. That's the most stable state. And so a covalent bond is very stable, and these electrons are held in there very tightly. Now, a lot of people will say, well, a semiconductor, such as silicon, germanium, and they always forget carbon, but carbon's a semiconductor too. They are between metals and nonmetals. Metals conduct, nonmetals don't. Semiconductors conduct a little. No, they don't. Because this covalent bond is just as strong as the ionic bond, and this will not conduct electricity. There's no free electrons to go anywhere. So let's redraw this in kind of a grid. Just draw a few silicon atoms. And just for simplification, I'm not going to draw all the electrons around there. I'll show you a drawing in a minute if you want to see it. Okay, there's some silicon there with all of its electrons. And a lot of times you will see physicists or engineers or whatever explaining this, they'll draw these little double lines between the atoms, indicating that there's covalent bonds, but I'm not going to do that. Just letting you know why they do that. So now you know. No, let's get rid of that one too. Okay, so what we have is all these covalent bonds. The electrons are held very tightly in their in the crystal structure, and no current can flow through it. But what would happen if we contaminated this with a little bit of something, let's say arsenic? Let's say these are all silicon atoms, but I'm going to put an arsenic atom here. And do you remember how many electrons arsenic has? It has 5. So I have 8 electrons around all these atoms, except this arsenic ends up with 9 around it because it has a 5th electron. So this arsenic atom gets 4 of its own electrons, 4 electrons from all of its surroundings, plus 1 left over that doesn't fit. So we have a free electron. I'll just draw this little dot here. And it doesn't really fit into the structure. Now it's going to be attracted to its corresponding proton in the arsenic atom, so it's not going to go very far, but it can wander around. Sound familiar? And let's go and just throw another arsenic atom over here. Just throw a few of them in there. And what does it have? It also has an electron that can just kind of float around. I'm just going around in circles, but it's just kind of there. It has to stay close to that arsenic atom. Otherwise, if some kind of energy came through and kicked it out, another electron would come and take its place. So it'll always have that 5th electron around there, but it's free to float around. What do you think would happen if we put a voltage across here? Those electrons would flow. New ones would come in and take their places. So when we dope this with impurities, in this case arsenic, but anyway, once we dope that with some impurities, we now, let's go throw another one up here, we can get those to flow. So when we dope it with these materials that have an extra electron, we call those donor materials because they donate an electron to the crystal structure. We now have something that conducts. Okay, now let's do that again. So we can do this without erasing and redrawing the whole board. Okay, let's get our atoms back here. 1, 2, 3. This time, once again, they're all silicon, but instead of adding impurities that have 5 valence electrons, let's add something like gallium, which has only 3, or aluminum. So let's use gallium because I like to say gallium. Gallium here, and another gallium there, and same 3 places. Gallium, gallium, gallium. So 8 electrons around here, 8 electrons around there, 8 electrons around everybody, but the gallium atom is 1 short. So there's only 7 electrons around this one. So there's a gap. How do I draw the gap? Well, here's a drawing here, and if you look carefully, you can see some gaps, but they're hard to see. But basically, I'm going to draw that as a circle. It's a place in the valence shell of the gallium atom where there could be an electron, but there isn't. So this whole crystal is missing an electron there. And remember that these elements that have a lot of electrons in the valence shell have this property called negativity. They're neutral because the same number of electrons as protons, but they call it negativity because there's a lot of electrons and it tends to attract other molecules there that can then donate their electron. So if there are any free electrons floating around, which there are many, that electron is going to want to go in there. But there's no force, there's no proton to hold it there. So basically an electron is going to kind of hang around. And that's going to happen with all these. Every gallium atom is going to have 1 electron that just kind of hangs around. Now there's a problem with this. Let me take it a step further and say if we put a voltage across here, positive to negative, what's going to happen? Those electrons are going to start flowing. But there's actually a problem here. If we try to start following these electrons, it becomes very difficult. Let me give you an illustration as to why. An everyday illustration for all of us who play golf, which does not include me. I played golf, I think, once. But I do know a little bit about the game, and I do know that at the end of each hole there's a green end, which is very smooth grass. Let's draw the green. You can tell it's green because it's black. And somewhere on that green is a hole. I'll put that right there. And of course, the ultimate goal is to get the golf ball in that hole. I like to say that the hole attracts golf balls, but my golfing friends don't think that's funny at all. So anyway, you're playing golf one Saturday and you come to the sixth hole, and there it is. Your golf ball is there. You hit the ball into the hole and score your hole and move on. Next day you come out, and as is often done, the groundskeeper has moved the hole. Now it's over here. They don't want everybody doing their golfing right around here. It's going to destroy the grass eventually, so they move that hole around the green, sometimes on a daily basis, just to keep it healthy. So the next day you come through, your ball ends up here, you putt in or putt out and score your hole and move on. Don't think anything of it, because they move the hole all the time, so the hole moved. Did that hole really move? Looks like the hole moved. No, of course it didn't move. A groundskeeper came in with a cutter, cut a plug of dirt from here, and where the hole used to be, took that plug of dirt and put it in the hole and cleaned it up so it would eventually grow out, and in a few weeks you would never see it again. But it sure looks like the hole moved. In fact, if you try to follow the grass plug from place to place as they move them around the golf course, well, they disappear. You can't really watch them. So what the heck? The hole moved. And so let's go back to our subatomic particles, back to our crystal structure. And so I said that there are electrons there, but it gets very, very confusing. Trust me, I've tried to explain it this way. Following the electrons, it does not work. So we don't follow the electrons. We follow the holes. So there are those holes. So let's say this gallium atom has an electron there, so I'll put a dot there instead of the hole because that hole is full of an electron. And let's say this electron drifts over and, oh, look, a hole, and pops in there. Now the electron's over there, and it's not in the other place. So what happened? The hole moved. The hole was here, the hole's there now. Hey, that's easy to see, just like the putting green. Looks like the hole moved. Looks like the hole moved here. In fact, it's more than that. Even on a physical level, the hole has the characteristics of a real object. So, for example, it has a negative mass. If that's probably the wrong way to say it, but if you push the hole that way, it goes the opposite direction. Can we call that negative mass? I don't know. But if you put a force on it, it moves the opposite direction. Of course, it's really an electron moving the other way, but it looks like the hole moved. And it's even subject to special relativity. If we get a whole bunch of holes moving together, and I'm watching those holes go by, they look closer together than when they're stationary. Or if I'm moving by the holes, they look like they're closer together when I'm moving by. I see them, I think they're moving, they're closer together, but when I stop moving, they appear to stop moving, and they're further apart. So they're subject to special relativity, just like a real entity. And so we don't follow the electrons in a material that has the extra holes. We follow the holes. Now, there's a name for these types of materials. The material with the excess electrons is called N-type material. So, extra electrons. I'll keep this short. A couple of extra electrons, mostly silicon, a couple arsenics. We call that N-type material. Why? Because it's sort of negative, but it's not. It's neutral because for every electron, there is a proton, so it's neutral, but there's electrons floating around, so we call that N-type for sort of negative-ish, but it's not really negative. The other one that has excess holes, and they can move around. Do they really move around? Yeah, for all intents and purposes, they do. These holes move around, But there's a deficiency of electrons. It's sort of like it's positive, but it's not positive because for every electron, there's a proton, there's a missing electron, but there's also a missing proton, which is why there's a missing electron. So it's sort of positive-ish, but not really, so we call it p-type. So there's the two types of semiconductor material, and of course I didn't mention the p-type material is conductive. So intrinsic silicon, pure silicon is non-conductive, but you put impurities that add electrons, that donate electrons, that becomes conductive. You put in materials that donate holes, then it becomes conductive too. Okay, now comes the magic. What we're going to do, I have them already there. There's some N-type material, there's some P-type material. Let's put them together. So I'll put an electron here and a hole over here to remind us that from here to the right is P-type material, from here to the left is N-type material. Now an interesting thing happens. I'm going to put another row just to help explain it. Extra electron, extra hole. When we put the N-type and P-type material together, these atoms have a lot of negativity, if you will. That's what they call it. There's 7 electrons around each one of these, and just like an atom that has 7 electrons in the valence shell, it's very attractive to other materials. What's going to happen? Well, electrons from over there are going to go hop and be in those holes. And let's make this electron go over to that one. So what happened? I had this electron go to that hole. Is the hole there anymore? Nope. Is the electron there anymore? Nope. There's no longer a free electron over here, and there's no longer a hole over here. And the same thing happened here. This electron went over and hopped over to that hole. Now it only happens near the junction because these electrons cannot go far away from their parent atoms. But as long as it's close enough, they can hop across and fill those holes. So in this area here, there's the junction. It's called a p-n junction. I guess I should have put the p-type over here and the n-type there. It's called a p-n junction. And near that junction is an area where there are no free electrons and no free holes because the electrons have gone and filled them. That's called, that area, I'm going to have to erase this to put the word there, is called the depletion region. So there are no free electrons or holes in that area. Is that going to conduct electricity? No. So we have an area that's non-conductive between two conductors. Sounds like a capacitor, doesn't it? I'm getting ahead of myself. We'll talk about that when we talk about different types of diodes. But the important thing is I now have a non-conductive area here. Now I'm going to erase this and redraw it to help us see what happens when certain things happen. So here's a block of silicon. There's our p-n junction. And what happens? I'll keep this side n and this side p just to be consistent. And so there's free electrons floating around here, free holes floating around here. But there's none in here because the electrons have jumped over and filled the holes. So we have a depletion region. Now what I'm going to do is put a negative charge on this side and a positive charge on that side. Basically, I'm putting in a battery with a negative terminal here and the positive terminal there. What's going to happen? Well, remember these holes move. Now, of course, it's the electrons moving, but don't even try to follow them. It'll just confuse the heck out of you. But remember, those holes will move, and it looks just like a real entity. Those holes are going to be attracted to this negative charge. So they're going to pull away from that depletion region, making the depletion region larger. Same thing's going to happen here. These electrons are pulled away, making our depletion region larger. So putting positive and negative, negative to the positive side, positive to the negative side, is only going to widen that depletion region. Is it going to conduct? No, we just have a bigger region that will not conduct. So let's take our charges away. Put our depletion region back the way it was. And I guess we redraw our holes and electrons here. Okay. Don't forget your depletion region. So there's our depletion region. Now we're going to put positive on the P side and negative on the N side. What's going to happen? Well, these holes look like positive charges, and they're going to be pushed away. So they're going to be pushed closer to the junction. These electrons are negatively charged, so this negative charge over here is going to push those electrons closer to the junction. Okay, so if we put negative on the P side, positive on the N side, the charges are pulled apart. Actually, we call these charge carriers. These charge carriers are pulled apart. But if we put positive on the P side, negative on the N side, they're pushed together. What happens if we make this charge big enough? Well, with silicon, that happens at about 7/10 of a volt. These holes and electrons are pushed close enough together that the electrons jump into those holes. What happens when the electrons jump into the holes? It's just like if you take a plug of dirt and put it in the hole at the golf course, the hole's not there anymore, is it? Well, those electrons and holes are now gone. And new holes and new electrons come in to take their place. And they're pushed toward the middle. And the electrons jump in the holes and they're gone. The electrons and holes are disappearing, and what we have is holes flowing in that direction and electrons flowing in that direction, and they disappear in the middle. Now, of course, what's really happening is the electrons are flowing in this direction, but like I said, if we try to follow those electrons, we'll become hopelessly confused. So let's just follow the holes on this side, the electrons on that side, so it appears they're being annihilated, and we just have more coming in. But we have hole current flowing that way on this side, electron current flowing that way on that side, but we do have current. And of course, it really is electrons flowing right through. So we now have a current flowing through there. So what do we have? We have an electronic check valve. If we put pressure on it, voltage, negative to positive, it will not flow, but we reverse that, it will flow. So we have what's called a diode now. Here's the symbol for our diode. Let me get the direction correct here. There we go. The arrow points in the direction of conventional current. The holes flow in the direction of conventional current. In fact, some people say, well, conventional current is hole flow. Okay, I'll buy that if you want to. I don't usually think about it that way. To me, it's just a fictional flow that works. But if you want to call it hole flow, works for me. Works in metals too. Some people say, oh, there's no holes in metal. Yes, there are. Talk to a physicist. The absence of electrons in metals, when the electrons move around, are called holes, just like these. It's a different mechanism, but they do exist. So if you want to say that conventional current is hole flow, more power to you. I just don't think of it that way. It's just not the way my mind works. But we now have a device that if we put positive here and negative there, we will get a current flow. But if we put positive here and negative there, we do not get a current flow. And that is the basics of how a diode works. Now, in the case of a silicon diode, once again, that flow starts to happen at about 7/10 of a volt. Really, it depends on who you're talking to. Some people say it starts at a half volt. Some people say it starts at 6/10 of a volt. Let's see why they say that. Let's do a quick graph here. So here is 0 volts. Here's our voltage, and this will be our current. I won't put any units on the current because it's dependent on the diode. But let's see, there's 0.5 volts, 0.6, 0.7, and I'm not going to draw all the numbers there, but if we look at the curve, as we push those charge carriers together, we get a tiny bit of current, tiny, tiny, tiny bit. So we get a tiny bit of current even when it's reverse biased. In fact, I got to mention these terms. When we have it biased so that it conducts, it's forward biased, pushes the electricity forward. When it's biased so that it does not conduct, it's reverse biased. I don't have the drawing there anymore, but I'll draw it real quickly here. Reverse the direction, but negative to positive, positive on the point, negative on the cathode, positive on the anode. It's not going to conduct. It is reverse biased. But if I flip those around, positive on the anode, negative on the cathode, it will conduct. It is now forward biased. So we get a little bit of current, a little bit of current. But once that depletion region is collapsed, which happens at about 0.5 of a volt, we start to get some conduction. So that's why some people say it's 0.5 of a volt. I said 0.7, which is what most people say, but it's really more around 0.5 of a volt. We get a little more at 0.6, but by the time we get to 0.7 of a volt, in fact, if you trace this line back, it should go pretty close to 0.7 volts. And so we get a huge cascade of current. So it's not linear like a resistor. A resistor, you double the voltage, you double the current. We get a straight line off of a resistor. A diode does not act that way. We get this logarithmic curve where no conduction, no conduction. At about 0.5 volt, it starts to conduct, and it's really conducting at 0.7 of a volt. Now, it's a myth that a silicon diode always has 0.7 of a volt across it when it's forward biased, because this is not going straight up. It's going at an angle. And if we go higher, we'll find it is more than 0.7 volts. It depends on the diode. Most of your small signal diodes will not get quite to 0.8 of a volt. No matter how much they're conducting, they'll burn up first. But some big diodes can get up to maybe 1.5 volts. But they're conducting a boatload of current when they do, 3, 4, 7 amps, whatever. But typically, most of the time you can look at the voltage across a forward biased diode, and it's going to be somewhere in here, more than 0.7, less than 0.8, somewhere right around in there. So 99 times out of 100, or maybe 9 times out of 10, you're going to find 0.7 volts across a forward biased silicon diode. So that's what everyone says. If this is a germanium diode, we can do the same thing with germanium. It's going to do this more like around 0.3 volts. So germanium starts to conduct and does that cascade much closer to 0.3 volts. So if you need a diode that has a smaller voltage across it, you need a germanium diode. Then there's Schottky diodes that have even less, but we'll talk about those in another video. So that's your diode curve as you forward bias it. Of course, reverse biased, nothing. It does not conduct. Except if you get the reverse bias voltage high enough, you might exceed what's called the peak inverse voltage, and it will start to conduct like gangbusters. That's why I draw that line. I mean, the negative current, what's negative current? Just current flowing the opposite direction. So if we reverse bias that diode and put enough voltage across it, eventually we reach the peak inverse voltage and it will start to conduct. And most diodes will be destroyed by that, but there is one diode that's made to work. The mechanism's a little different, but it looks the same, and it happens at a much lower voltage, and that's called a Zener diode, which we'll have a whole video just about Zener diodes, so we won't talk about that now. So watch out for that breakdown voltage. It might be 50 volts, might be 100 volts, might be 1,000 volts, depending on the diode. But every diode has a peak inverse voltage that you do not want to exceed when it's reverse biased. So that's mostly what we need to know about semiconductors, and I talked about diodes. We'll talk about transistors in their own video. So what we have are our semiconducting materials, which are carbon, silicon, and germanium. We put them together into a block of material. We get what's called a covalent bond, where there's 4 electrons around each atom, but in the covalent bond they have 8. Remember that atoms like to have 8 electrons around there, so they're stable. And so when these semiconductors form this covalent bond in a block, they are non-conductive, but we put impurities in there which cause the characteristics that we talked about before, creating the depletion region when charge carriers jump from one side of the junction to another. We reverse bias it, it pulls those charge carriers further apart so it doesn't conduct. We forward bias it, we put them closer together. And if we get it forward biased to a particular voltage, about 0.3 volts for germanium, about 0.7 volts for silicon, it will start to conduct like gangbusters. So that is what you need to know about semiconductors. Once again, it's not going to help you do any circuits, but it's something you're expected to know, and I hope you found it interesting. So if you found this useful and informative, please give me a thumbs up. Helps the channel a lot. And to help me put these videos online, please go to Patreon at the link on the board here and pledge your support. Couldn't do it without my patrons. And a big thank you to my patrons who are making this all possible. And thanks to everyone for watching.